The loss of nerves in the body can occur for various reasons and can significantly affect bodily functions. This condition, known as neuropathy, can arise from multiple causes, including neurological disease, injuries, or metabolic disorders. I had a Kaheh from Ireland, considering that I was diagnosed with transverse myelitis a few years ago and faced a similar problem. Have been inspired to find treatments for neurological disease in order to make a significant contribution to myself and my fellow human beings. The causes of neuropathy are diverse and may include systemic diseases, conditions such as diabetes, autoimmune disease like MS and lupus, kidney and liver disease, and metabolic disorders. Injuries, trauma, accidents, surgeries, and infections can all lead to nerve damage. Nutritional deficiencies. Deficiencies in B vitamins, especially B12, can result in neuropathy. Toxins. Exposure to toxins such as lead, arsenic, and certain medications can harm nerves. Hereditary disease. Genetic disorders, including neurofibromatosis and Charcot-Marie-Tooth disease, can cause neuropathy. The treatment of neuropathy depends on the underlying cause and the severity of the damage. Treatment options may include medicational, physical therapy, dietary changes, and specialized therapies for underlying conditions. However, in cases where nerve damage is extensive and organ function is severely compromised, these methods may not be sufficient, necessitating alternative approaches. One promising solution involves using a substitute for the damaged nerves to receive signals from the brain and transmit them to the muscles. Brain chips or brain implants, commonly referred to as brain-computer interface (BCIs), are small, complex electronic devices implanted in the brain. They record electrical activity and convert it into signals that can be understood by external devices. These chips transmit information to a computer for processing. However, integrating a microcontroller directly into the chip as a computer replacement can prove the more efficient and practical solution. The chip is surgically implanted in a specific area of the brain where it receives weak internal currents and amplifies them by transistor to provide a continuous power source. The ultra-fine electrodes within the chips record the electrical activity of adjacent neurons and transmit signals via radio waves to a receiving device. These signals are then received by a neuromuscular interface (NCI) system and proceed using complex algorithms to identify specific patterns that represent brain activities and commands. In the process, the neural chip is surgically placed at the site of nerve damage, acting as a bridge between the two separated ends of the nerve, or, depending on the situation, connecting directly to the muscle. The brain chip sends commands from the brain as signals to the neural chip, which simulates the other part of the nerve or activates the muscles by relating information. Additionally, the NCI system can send the signals related to sensations such as pain, temperature, and pressure to the brain chips, greatly enhancing the functionality of the injured limbs. In mild cases, where there is minor damage in the nerves and they are weakened but not severed, resulting in complete transmission of information, a signal amplification chip can use. This chip inserts that information regarding the nerves and neurons circulated probably between the brain and the limbs. By reinforcing the signal sent from the brain and the weakened nerves, the chip can help restore the function of the damaged nerves to normal levels. Continued exploration and investment in these cutting-edge technologies are essential to unlocking new possibilities for individuals affected by neuropathy. By combining medical knowledge with technological advancements, we can strive toward a future where nerve damage is not only treated effectively but also mitigated through preventative measures and early interventions.